So for one-dimensional heat conduction, our objective is to determine the temperature distribution. In one-dimensional steady-state problems, a temperature gradient exists only along one coordinate axis, and the temperature at each point is independent of time. So we have our problem is we're going to have a plain wall here and subject to uniform heat generation. So you have heat flow happening here, and you have the left face and the right face, okay? And what we're going to be looking at, let's zoom in on this area, consider this in between this domain, and this is kind of a zoom of that. So we have our left face here, our right face here, and then we consider basically like a section, okay, a section of that material. And we give it a dx, okay, so this is the x direction, and we're going to look at a dx in there. And then we have our various values of the heat transfer, the heat flux, the area, and so forth that we're trying to solve. So we have one side and the other side. Okay, so we're going to have this dq dx times x that represents the change on the other side. So the area is the area normal to the direction of the heat flow, and Q, watts per meter cubed, be the internal heat generated per unit volume. So we can write that down in equation form. So we have the heat rate, that's the heat flux times the area. Okay, we have the control the volume plus the heat rate generated. Okay, so this is the generated QA times dx along that length that it's operating, equals to the heat rate leaving the control volume. Okay, so there we're going to have the original plus that change in Q. So we can write Q, we can add those up, QA plus capital QA, that's the internal heat generated, times dx is equal to what's leaving, which is Q plus how Q changes over dx times dx, and that's going to be multiplied by the cross-sectional area. So these terms actually cancel out, okay, and so we're left with QA dx is equal to dq dx dxa. And of course we see those things cancel out, so canceling out QA both sides, we actually get internal heat flux is equal to dq dx. So we have Fourier's law. Remember, that is Q is equal to negative K dt dx. So then we can substitute the Q into that Q. Okay, and we're going to left with this gives, we're going to have Q is equal to d dx, and then it'll be negative K dt dx, or d dx K dt dx plus Q is equal to 0. Now, a couple of notes here. K usually a function of x, and also this can be solved appropriate boundary conditions. So that's actually our governing equation for the one-dimensional heat conduction problem. Okay, so what kind of boundary conditions could be applied? So we have boundary, we typically have three kinds. Typically of three kinds. One is a specified temperature. Second one would be a specified heat flux. Or insulation. And the third one would be convection. So, for example, consider wall of a tank containing hot liquid at temp T0 with an airstream of temp T infinity passing on outside. The boundary conditions for this problem are T x equals 0 is equal to T naught Q at x equals L is equal to H TL minus T infinity. So this one would go here, and this one would be here. Okay, so those are typical boundary conditions you could have for this type of problem. Now, how do we actually implement that in the finite element method? What's different? Well, it actually is very similar. It's the FE finite element is similar to one-dimensional linear and quadratic truss. So for example, we have a two-node element with linear shape functions. So we have T of psi is equal to N1 times T1 plus N2 times T2. Okay, so in this case, if we look at our problem, like T1 is equal to T0 over here, right? So we discretized the problem we just looked at the last slide, and we have that boundary condition. So we know that value there. We can also write this thing in matrix form, so T and the temperature of the element, so two vectors, and in this case N is equal to 1 minus psi over 2 and 1 plus psi over 2. Okay, so they're the same kind of shape functions we use with the truss, and we would have temperature in the element is equal to T1 T2, kind of like that to be like a local displacement vector, if you remember that. The psi mapping functions are the same, so psi is equal to 2x2 minus x1, x minus x1 minus 1. We talked about that in the very beginning of the course with the one-dimensional case. And the resulting equations are very similar with the way we apply the chain rule. So of course we can get d psi, and that's going to be equal to 2 over LE dx. And also we have the temperature, derivative temperature with respect to x is equal to dt d psi dx. Okay, this is again the chain rule. So then we can substitute in our our d psi dx is equal to 2 over x2 minus x1. Okay, and it's going to be then dt d psi, so we would substitute in our t sub psi over there, and we have d eta d psi times t sub e. That went there, okay, and that went there. So then we have the derivatives of the shape functions, which we need to figure out. So for that, we do dt dx is equal to 2 over x2 minus x1 is right again, dn d psi t e. So from that we get 1 over x2 minus x1, negative 1 to 1, times te. Okay, so dt dx is equal to bt te. Okay, where bt, this is the derivatives of the shape functions for the thermal part, is x2 minus x1, negative 1, 1. We should be pretty familiar with that because that was the same in the 1D. All right, so now we can use this information to actually get the thermal stiffness of, we call it thermal stiffness because it's very similar to a stiffness matrix. So when we get down here, we have thermal stiffness. I'll put that in quotation marks at the element level. So K sub T is equal to KE over LE. We're going to have 1, negative 1, negative 1, 1. And the force, the thermal, call it the thermal force value is R, and we would do a Q. This is kind of like the body forces, if you want to think about that. And that was where we used that capital Q that we had before. We have the heat source or sink, the LE, length of the element, over 2, and 1, 1. So the basic idea, by the way, this is also thermal conductivity. Elemental thermal conductivity. Hopefully you can see the similarities between this problem and the structural problem. Okay, so that's the elemental stiffness, and of course after that then you go into the assembly process, which is very similar to what we would do. We're going to use the next segment to sort of summarize all this and wrap up the thermal components.